We are going to talk about topic 4B, which gets us thinking about how you represent phase equilibrium. So we're going to start with pure substances and slowly move into what happens if you have a mixture. So in this topic, we're only talking about a pure substance and how a phase diagram represents what phases you can expect to find at different values of temperature and pressure. So, phase diagrams of pure substances. So the key idea is that at equilibrium, the molar Gibbs energy of a substance is the same in all the phases in which it occurs, which makes sense because if it wasn't, you'd move into the phase with the lower molar Gibbs energy in order to essentially maximize entropy. So if at equilibrium all the molar Gibbs energies are the same, then the phases aren't going to go one way or another. They're going to go back and forth in a dynamic equilibrium. So the phase diagram, which you may have learned a little bit about in Chem 107, is just a diagram for a substance that right here shows you. It has axes of pressure and temperature, and it just shows you what phases are present. It shows you have solid, liquid, and gas here, and the lines represent places where the phases would be in equilibrium. So you'd be passing, for example, from the solid phase into the gas phase if you increase the temperature along this line. And similar for solid to liquid and liquid to gas. Can't see it out on this diagram, but it just represents, so a phase diagram is generally created experimentally, but we're going to see that you can actually understand how you could calculate or what some of those lines depend on. So the phase boundaries, for example, when you're talking about a liquid gas boundary, then you're really talking about the vapor pressure. So when you look at a point on this line where the liquid's in equilibrium with the gas, by definition, the vapor pressure is the pressure of a gas that's in equilibrium with a liquid in a closed container. And so essentially you're measuring the vapor pressure of that liquid on that phase boundary. Here it's not a vapor pressure, but it's still the equilibrium between a solid and a liquid. So this just talks a little bit about the different regions. Sublimation, where you have solid going straight to a gas. And this is the important point on this page, is that any point lying on a phase boundary represents a pressure and temperature at which there's a dynamic equilibrium between the two adjacent phases, a state in which a reverse process is taking place at the same rate as a forward process. So when you think about those boundaries, when something is vaporizing, for example, you have the transition from liquid to vapor, and when they're in equilibrium, they're going back and forth at equal rates. So you have the two phases in equilibrium. This diagram at the bottom just shows you how you create a phase diagram. So remember that if you're adding heat to a system, and in this situation, we're cooling it off. So we heated it up, and then we're cooling it off at a constant rate. And so first, whatever phase you have just changes temperature as a function of the heat capacity. And then anytime you get to a phase transition, the temperature stays constant as the phase changes. If you think about that possibly as liquid water or gaseous water condensing to a liquid, then during that process, the temperature is staying constant because you're creating those hydrogen bonds. So even though you're pulling heat out, you're not changing the temperature. So all the plateaus would be places where you'd know you'd put a phase boundary on your phase diagram. And then these regions essentially tell you what the heat capacity is of whatever phase. So this phase has a different heat capacity than this one, because the slope of the line, how temperature changes with the change in energy is different. So we want to look at how we could theoretically understand those phase boundaries. So once you have an experimental phase diagram, you can think about understanding something about the properties of the system. So we are going to derive this equation right here. And we'll go all the way to a derivation of this equation and this equation. So I'm going to just think about where those boundaries are. So we've already looked at this relationship for any one phase. We derived the relationship between pressure and temperature. And so we saw in the last section that was true, that the Gibbs free energy changes as a function of pressure and temperature, and that the proportionality constants, or how they change, is entropy and volume. So if we have one phase, so we'll say one is just a phase of our substance, and we're going to talk about molar. So little subscript means the molar Gibbs free energy changes as a function of volume, pressure, entropy, and temperature. Then we can write the same thing for the other phase. And what we know is the change in Gibbs free energy, if we're going to stay on that line where the two phases are in equilibrium, for them to be in equilibrium, this needs to equal this. The Gibbs free energy has to be equal to each other for the two phases. Therefore, the change in Gibbs free energy has to be equal in order to stay on that phase boundary line. So if we're at equilibrium, then it's going to be true that those are equal. And so if I then set this equal to this, I get has to be equal to molar volume of the second phase, entropy of the second phase, and the change in temperature. So now we're just going to group the terms together. So pull all the entropies to one side. So let's see. Yeah, if I bring the entropy over to this side, negative goes away. Now if I take the volume to that side, oops, P. And then let's just group them, and we'll call this the change in entropy for the transition. So the change in entropy for the process of going from phase 1 to phase 2. So then what we will have is change in the transition entropy. And you pull those terms out, they're each times delta T or dt. And then over here, we'll have the same thing, change in the volume for the transition. And each of those is times the differential of pressure. So now we can just look at what the slope of that line should be. So how should pressure change with temperature? Take the dt over here, and it should be equal to the ratio of the change in entropy over the change in volume. So that tells us what the slope of a line should be to keep two phases in equilibrium. So when you look at an experimental phase diagram, you should be able to get some information about the entropy of the two phases and the molar volume of the two phases. So if we're at equilibrium, you remember, so if we're at the temperature of equilibrium for the process, then the entropy change is just related to the enthalpy change by that ratio. And so now we can generalize this and say dP dt is equal to, I'll plug in this, This gets a little bit confusing how the book writes it, but I'll make sure it's clear here. So what this is saying is I plugged this in, but I have to have the delta H at the transition. So it has to be a function of the transition temperature. And then when I put in delta S, delta H over T, here's my T, and then I still have my delta V for the transition, which is also for that transition at that transition temperature. So that's just showing with the parentheses, not that you're multiplying again by the ratio of temperatures, but just that each of those is a function of the transition temperature. So let's go back here. And look at self-test. Self-test 4B.1. So it asks us in self-test 4B.1 to estimate the change in temperature over a change in pressure for water at its normal boiling point using the information that's in the table. It said don't use Troughton's rule, which I never use anyway, which basically says the entropy change is about the same for every transition from liquid to solid or liquid to gas. But we'll just use the exact things because we have them in our table. So if we want to estimate delta T over delta B, or delta T over delta P, we know that this is equal to dP dt. And so to estimate, we're going to say that we're going over a small temperature change. And so when we look at this ratio, we can estimate a differential, an infinitesimal change in pressure and temperature as being a delta. So this was our equation right here that we derived. So now we're just going to flip it because it wants delta T over delta P. So we'll flip it. Everything that was in the denominator is now in the numerator. The temperature at which water is in equilibrium is water. Yes. At the normal boiling point of water, so that's 373.2. The delta H is 40.7. The standard state pressure in your book is 1 bar. So you have delta T over delta P is going to be that temperature for the transition. It's going to be, this is an approximation, but it's a good one, that delta V for the vaporization process is really just the volume of the gas, because the volume of the liquid is so small. For a mole of water, it would only be 18 milliliters versus for the gas, we got 3.1 times 10 to the minus 2 meters cubed. So you can estimate that delta V to be just the volume of the gas. And then you're going to divide it by the delta H, and I changed it into joules. So I'm using everything in SI units except the bar because it's going to cancel. So if I use the gas constant in meters cubed bar over K mole, multiply by the temperature, I want the molar volume, divide by 1 bar, I end up with the molar volume of 3.103 times 10 to the minus 2 meters cubed. When I plug that into this, I end up with, let's see, yeah, I end up with meters cubed over joules. And so that gives me the units for my delta T over delta P in Kelvin over Pascal. And so you could think about the equation for any line on a phase diagram using that equation. But we want to think about actually integrating it in case we're not going over a small enough temperature range. So we are going to look at how vapor pressure changes with temperature. So now, because a gas pressure changes a lot and we don't want to estimate it, we want to have a better idea of how they change with how pressure and temperature impact each other. So we're going to start out with our equation. We want to know how the vapor pressure changes with temperature. So we start out with our equation, and we are going to replace the delta V for the vaporization process with just the molar volume of the gas. That's a very good approximation. And then we're going to say that it's a perfect gas. So the molar volume of the gas will be RT over P. And so we're going to go back here, and where we saw the molar volume of a gas, we're going to put in RT over P. And so we have delta H for vaporization over, that's hard to read right there. This says dP dt equals delta H for vaporization over T times RT over P, which was the volume. And so if we just rearrange that, the P will come up to the top. I think that looks kind of messy too, so I'm going to redo it. So this P that's down here comes to the top, and I get RT squared in the denominator. So delta H for the vaporization process times pressure over RT squared. And now we need to integrate it. So you need to separate the variables, get the P's over with the dP, and multiply the right-hand side by dt. So take the dt over to that side. And so now when I integrate this one, remember the integral of 1 over x is natural log of x. So from P initial to some new vapor pressure. So it's going to be natural log of P prime over P. And on this side, I can take the delta H of vaporization over R out front. So I'm assuming that I'm going over a temperature range still that's not huge, because I'm assuming that delta H doesn't change with temperature. Then the integral of 1 over T squared from T to T prime gives you 1 over T minus 1 over T prime. And that's your equation that you can then use essentially to find all the points on the liquid to vapor line of a phase diagram. That's the derivation that we just went through. And then just reminds us that vapor pressure always increases with temperature. And so for a given temperature change, the greater the enthalpy of vaporization, the greater the change in vapor pressure. So that's exactly what it's saying, that the vapor pressure change is proportional to the delta H of vaporization. So that's finishing the derivation I just did. So go ahead and do self-test. Yeah, self-test 4B.2. And then when you get to the next page, I just want you to read. These are some experimental phase diagrams. Might even be the same ones you saw in Gen Chem. They usually give water and CO2. Some of those that have unique phase diagram properties that we can talk about. So read through the rest of section B. And when we come to class, we'll go over those phase diagrams on the board. And that is all of that section. So make sure you read that and understand maybe put all the definitions of the terms that you see in there in your notes, and just be ready to talk about those phase diagrams.